Agora. Ok. Bom dia a todos. Dando prosseguimento à programação do quarto workshop de computação quântica, nós passamos agora a palestra intitulada Algoritmo Quântico para Otimização Multiobjetivo, que será proferida pelo professor Marcos Villagra, da Universidade Nacional de Assunção do Paraguai. Professor Marcos é PhD desde 2013 em computação teórica pelo Instituto Nara de Ciência e Tecnologia do Japão, foi pesquisador da Sociedade Japonesa para a Promoção das Ciências e fez de 2013 a 2015 seu pós-doutorado na Universidade de Fukui. Desde 2015 ele é professor e pesquisador na Universidade Nacional de Assunção, e dentre os seus interesses estão complexidade computacional e algébrica, criptografia, computação e informação quântica, jogos combinatoriais, teoria de autômatos e algoritmos algébricos e espectrais. I will present Marcus in English now, and following the fourth quantum computing workshop, we received Professor Marcos Villagra, that will talk about quantum algorithm for multi-objective optimization. Professor Marcos received his PhD in theoretical computer science from Nara Institute of Science and Technology, Japan, in 2013. He was a research fellow of the Japan Society for the Promotion of Science and a postdoc research at the University of Fukui from April 2013 until March 2015. Since April 2015, he is a full-time research professor at the National University of Asunción, Paraguay. His research interests are computational and algebraic complexity, cryptography, quantum computing and information, combinatorial games, automata theory, and algebraic and spectral algorithms. Questions could be done by YouTube chat and will be answered at the end. As perguntas podem ser feitas pelo chat do YouTube e eu as passarei para o professor Marcos no final da palestra. Welcome, Marcos. Thank you for accepting our invitation. It's a pleasure to have your talk in our meeting. Have a nice talk, and at the end, I will address you all the questions doing by the audience. Thank you.
Okay, so I'll start now. Well, first of all, thank you very much for the invitation. And it's really nice to know that these kind of events are starting to be done more often here in South America, because we have, in South America, we have a very small community in quantum information science in general, right? So let me know. I think everything is going well. So the screen is being shared. So well, let me start. The title of this talk is Quantum Algorithms for Multi-Objective Optimization. Just let me give you a brief presentation of what we do. I'm from the National University of Asunción in Paraguay, and basically this is the building where I mostly go there every day to do my work, my office work. Right now I'm at home, right, for this talk, but I haven't went there today. And we have like I'm working for one school, the National University of Asunción, and we have this is the main research area we do here in the Núcleo de Investigación y Desarrollo Tecnológico of the university, right? I work, of course, in theoretical computer science. This is a small group we have in theoretical computer science there, and some of these students already graduated, so I have to update this list. And mostly, we're working mostly around these areas, right? I don't come from physics. I come from mathematics and computer science. So my main research field is computational complexity. So quantum computing is just one part of computational complexity for me, at least, right? So in this talk, what I'd like to talk is about how to solve multi-objective optimization problems using a quantum computer. Okay, but to start with before starting to talk about multi-objective optimization, because it's not a very well-known concept, so let me first start with the main quantum technology we're going to use to solve these kind of problems, and this is called quantum annealing. Okay. First, let's review a fast review on what is a combinatorial optimization problem, right? So we have a set of feasible solutions, right? And each solution has an assigned cost to it. And what we want to do is to minimize. All we want to talk in this, we know lots of generality about minimization problems. We want to minimize an objective function subject to some set of constraints, right? And you know that if you know a little bit about of optimization problem, there are several kinds of optimization problems, like linear optimization, quadratic optimization, convex, concave, positive semi-definite optimization, and so on, right? And combinatorial optimization is when the domain of the objective function is discrete or finite, right? And you know that, for example, if we're trying to optimize a function like this, we have a global minimum or several global minimums and local minima also, right? Local minima are points like this, right? There's not really the smallest, the solution with the smallest value, but is a local minimum is a point where is sandwiched between between two mountains, like here, right? So in computational complexity, we care a lot about what we call NP-hard optimization problems. And an NP-hard optimization problem is a kind of optimization problem where when normally finding the optimal solution is really hard. Hard means here that it takes a lot of computational resources to find that solution. Like you take a lot of time or a lot of memory, right, to find that solution. But if I give you the solution, it's easy to verify. Like, for example, to check the value of a feasible solution, that you can do it really fast. So that's one. That's are the characteristics of NP-hard optimization problem, and that's the kind of problems I'm going to talk here. I want to be dealing with we're solving optimization problems in a quantum computer. We want to solve actually NP-hard optimization problem because actually the most of the natural problems that occur in real life are that kind, right? So let me just talk a little bit about classical simulated annealing. So simulated annealing is an algorithm. It's what the people in artificial intelligence call a meta-heuristic or a heuristic algorithm. And the idea in simulated annealing is to simulate the annealing process of things like metals and ceramics and things like that, and they try to simulate that on a computer in order to solve optimization problems, right? And it turns out that kind of algorithms, there are a lot of algorithms in artificial intelligence that are inspired in nature. That's why they use simulated annealing, and actually it works really well, right? But the only problem it has is that it gets stuck a lot in a local optima, and there are other improvements you can do to algorithm to avoid that kind of things. So this is the algorithm. I'm not going to explain this in detail, so I'm just going to pass it. So what is quantum annealing? Quantum annealing. I hope that you can read Spanish here, right? Most of these parts in Spanish, other parts have it in English, right? So the idea of quantum annealing is that it uses quantum tunneling to solve optimization problem. And the idea is, you know, that quantum annealing is based on the Quantum Adiabatic Theorem that was discovered at the beginning of the 20th century, maybe the 30s. I don't remember the exact dates, probably 20s. I think our original paper was by Fock. And here we have a Hamiltonian that has normally this form. And we have what we call a final Hamiltonian and an initial Hamiltonian. And normally the way And what we want to do with quantum annealing is to encode that optimization problem into the Hamiltonian. So in the following way, for example, so take for example our Hamiltonian, and we construct this Hamiltonian by if f is the, for example, the function we want to optimize, what we do is to encode this function like this, right? It's on basis, right? So all the solutions of the function, all the points in this of the function goes in the diagonal of this Hamiltonian with respect to some basis, right? And you know that these have some eigenvectors and eigenvalues, right? Of course, if I put the objective function like this into the Hamiltonian, the values of the function are the energy of the quantum system, right? So if I want to find the ground state of this Hamiltonian, what I would tend is the minimum solution to this to the optimization problem and encoding to the Hamiltonian, right? And here's where adiabatic evolution comes to play. Here I have the exact paper from Born and Fogg in 1928 about the adiabatic theorem, the first report of the adiabatic theorem. And here you have the Heisenberg's Schrodinger's equation, and the idea here in the adiabatic theorem is that if you have a Hamiltonian that depends on time, say, and the idea is that if you start your system in for example, in the ground state of this Hamiltonian, and you let it change for sufficiently long time, when you measure at the end, right, you will obtain with high probability the ground state of h of t. So that's the foundation of of adiabatic evolution, right? And the time it takes to get from 0 to t actually depends on the eigenvalue gap, which is, I mean, that's the two smallest energies of the Hamiltonian, right? So we use that principle to construct a quantum algorithm that we call the quantum adiabatic algorithm. And the adiabatic algorithm works like this. First, we construct an initial Hamiltonian, which will be the Hamiltonian at time 0. Hamiltonian, each one is the final Hamiltonian, right? That will encode the optimization problem. We construct then a Hamiltonian H0, which will be the initial Hamiltonian. And normally the physicists I know, they want some initial Hamiltonian that is easy to prepare in the lab. And then what you do is to change from H0 to the final Hamiltonian really slowly using the Diabatic theorem, and then you measure here at the end. If you started in the ground state here, with high probability, you will find yourself in the ground state of h of t here, right? And the ground state encodes the solution to encodes the optimal solution to our optimization problem. Then we can obtain with high probability the solution we are looking for. So that's the idea between that's the idea of the adiabatic algorithm. The adiabatic algorithm was discovered by, I don't remember the name of the authors, in 2000. There's a paper in arXiv. I have the reference right now. It's been using a lot, especially now with the NISQ era of quantum computing, right? And one way to realize that the quantum adiabatic algorithm is using quantum annealing, right? And quantum annealing has been implemented by this company called D-Wave. And I'm going to explain a little bit about what they are doing, right? So we have in the D-Wave architecture, we have two parts, right? We have a quantum chip, which is actually the chip that implements quantum annealing. And we have an interface to the quantum computer, right? And the idea here is that what you do is you use this interface called SAPI, which is based on Python. And what you do is to load using SAPI, the SAPI using you load the program into the quantum computer, and SAPI sends it to the physical quantum chip the problem you want to solve. This, of course, only works. This is the quantum annealing is not a universal model of computation, and it can only solve optimization problems, which I'm going to explain right now. And so in general, this is the model we use to to solve optimization problems using quantum annealing. So we start with some instance of some optimization problem. We transform it to the Icing model. I'm going to explain in a moment what is the Icing model. The Icing model is the only thing that the quantum annealing or the waves quantum annealing can do is to solve the Icing model, finding the lowest energy configuration in the Icing model. And what we do is first transform our optimization problem to the Icing model. We extract there some numbers. I'm going to explain what those numbers are. We load those numbers into the quantum computer. Then the quantum computer see those numbers, do its magic, and it gives us the solution to our optimization problem. That's basically the how it works. So what's the I kind of looking a little bit about the commentaries here. So that's a good question, and we actually don't know. We still don't know how efficient is the quantum annealing model of computation. Right? People expect that it's fast, but we don't really know how fast. There are no theoretical evidence. It's really hard to prove things in this model of computation. It's been a lot of research. People are not really don't know, right? And the experimental side, it's really hard to compare, right? Because how do you compare? You can measure time. Let me explain a little bit there, a little bit more how the quantum computer, this model works actually, to get back to this point, right? That's a really good question, right? So so what's the Icing model? We have, we take a graph G, right? B is the set of vertices and E is the set of edges, and we have a weight for each vertex, and we have a weight for each edge in the graph, right? And like I said, I'm not a physicist, but basically this is, I know physicists use this to model some magnetic problems, right? What the physicists care about, right? And here is like you want to find a configuration of values for this graph where it minimizes the following function, right? So each variable Si can only take values from +1 and -1, right? And we have these coefficients, right? Hi and Ji, which I define it like this. And we want to find the configuration of -1 and +1s that give us the smallest possible value of E here, right? This is the optimization problem that I care about. And this is, it's been proven many years ago that this is an NP-hard optimization problem. So, and it turns out that the Icing model is a particular kind of a very well-known model of optimization called Kuvo, right? Kuvo means quadratic unconstrained binary optimization. Here means, the variables in the Icing model is ±1, and the Kuvo is 0 and 1, but it's very easy to change, go from ±1 to 0, 1, 1, 0, 1. So it's basically the same. In Kuvo, what we have is just a single optimization, is a single objective function, but with no constraints. So this is exactly like this, right? There are no constraints. I just have a single objective function that I want to minimize here. Okay, and this is the Hamiltonian of the quantum annealing architecture of the wave, right? This is the here we have the very well known matrices, right? Sigma so I, sigma so 1, 2, 3, right? We have the coefficients Hi here, Ji sub j here. This comes from the Icing model. Excuse me. So, and the idea is just to use this Hamiltonian to encode our optimization problem that we want to solve, right? And and the idea is, again, I'm repeating here the algorithm of the of quantum annealing here. Just to remember, this is very important, right? Remember that first we construct an initial Hamiltonian, a problem Hamiltonian. The problem Hamiltonian will, or final Hamiltonian will encode the solution to our optimization problem. Then we construct an interpolation between the initial Hamiltonian and the final Hamiltonian. I'm going to show you in a moment how you do that. And then you just let the system evolve, and then you measure, right? The key here is to how we encode our problem into the final Hamiltonian. I show you one way to do it, and another problem is how to construct the initial Hamiltonian. People really don't care too much about the initial Hamiltonian. The only thing that you want is that it's easy to construct in the lab. It doesn't have to commute with the final Hamiltonian, because that's one condition of the Adiabatic theorem. So here we are. This is how we interpolate both Hamiltonians, right? Just a linear interpolation, very simple. And the variable s, t, remember, is the time. So what we do here is to change. S goes from 0 to 1, actually, and takes all the real numbers between 0 and 1. So again, I always telling this several times, because this is the main key here, right? So we initialize our quantum algorithm by giving it the coefficients of the Icing model, the ones I mentioned before, right? H to I and J to ij. These are the weights on the vertices and the weight on the edges, right? And then you let it just do its thing, right? The annealing process, you measure the qubits, and normally you have to repeat this several times, because the answer is probabilistic. So you need to get the answers several times in order to have a final answer with high probability. And this is why it's really hard to prove anything about the time complexity of this model of computation, right? And just, I mean, people still don't know. You can find several papers trying different kinds of interpolation techniques to try to put an upper bound on the running time of this algorithm. It's more experimental, and that's common in heuristic algorithms also, actually, right? And definitely the quantum annealing algorithm falls into that category also. So just I want to talk a little bit about the machine here. Here you can see the arm of the quantum annealing computer, right? And the thing here's the quantum chip, right? And it looks like a grid like this, right? And each square is something like this, right? And the qubits are here, right? And they are coupled like in this way, right? So you can see that you have 4 qubits here and 4 qubits here, and this is each crossing point here is a coupling between the qubits, right? This is the way they couple, and the way they implement this qubit are superconducting flux qubits, right? And they use the current to encode a spin, the current on this this wire to encode 1 or 0 here, right? And I know that when these superconducting materials gets into the correct temperature and it becomes superconducting, you can actually start creating a superposition of the qubit there, right? So abstracting a little bit this model, what we have is that the Q-chip is a graph like that looks like this, right? And people in D-Wave call this the Chimera graph. So it's a bipartite graph that is a K44 bipartite graph. This means that a bipartite graph is a graph that you can separate in 2 halves, let's say, and all the vertices in 1 half are not connected. There's no edge between those vertices on the halves, on each half, but they are connected between the halves, each half, right? So so if you connect each square in the quantum chip, is a graph like that looks like something like this, right? And this is what people call the Chimera graph. So again, how do we program these quantum annealing computers, right? Again, we choose an optimization problem, we transform the optimization problem using a technique known in computational complexity as a reduction. We transform the optimization problem into the Kuvo or Icing model. And here, normally, you have to do some other stuff, like, of course, when you transform the optimization problem, you get the energy function of the Icing model. Then normally, that objective function is normally it's a polynomial, but it's not of degree 2. You wanted to have degree you want that polynomial to be of degree 2, because it needs to model this the graph, right? And normally, if the polynomial of the Icing model is not of degree 2, you have to use some techniques to get the polynomial of degree n, say, to degree 2 by adding extra variables, for example. And then you can construct a logic graph from there. Once you have that polynomial of degree 2, you get actually a logic graph of the Icing model, and you can then use that graph to what we call in graph theory embedded into the Chimera graph. I'm going to explain a little bit more what is a graph embedding from graph theory, right? Okay, like I said, normally when you transform your optimization function to a polynomial, because you're trying to transform it into the Icing model, it doesn't have a degree 2. So you can use techniques to transform that greater than 2 degree polynomial into degree 2 polynomial. And there are two well-known methods to do that. I'm not going to go into details here, but you can do it, right? I need to spend more time later in the multi-objective optimization part. It's already 30 minutes. So one is called the Friedman method, and it's called now there's another method called the Ishikawa method. There's a very simple techniques just to take n degree polynomial and transform it to a 2 degree polynomial by adding extra variables, right? So again, but this is the key, right? This is the key process and how we solve optimization problem, because the only thing that the quantum annealing computer can do is solve optimization problems. So now, what is a graph embedding? Again, let me repeat again. What's the process? This is very important. You start the optimization problem, transform it to an Icing model, and when you have when you obtain the degree 2 polynomial, you obtain a graph, a logic graph. And then this logic graph has to be embedded into the Chimera graph, right? Into the physical architecture. You have some logical qubits, and you want to embed those logical qubits into the physical qubits. That's basically the idea here. And we do that using minor embedding. First, what is a minor, right? A minor is, for example, H is a minor of G. What does it mean? It means that H was obtained from G by doing 3 operations. Deleting vertices, deleting edges, and contracting edges. How do I obtain H from G? For example, I can delete this edge here, this edge here, and then make a contraction here, right? Here and here, and you get this star, right? If I can obtain a graph using those operations, I say that the new graph is a minor of the original graph. So H is a minor of G because I only use those operations, right? So now, once I obtain the graph, of course, that corresponds to the Icing model, I need to that graph actually represents the logical qubits that are interacting in the Icing model, and I need to embed that into the physical qubits, right? And let me show you with this is everything explained here, but let me show you with an example here. For example, what happens if I want to embed this graph into the Chimera graph? I'm going to embed only this triangle into 1 square of the quantum chip, right? And what you do is, for example, for each, for example, you take these vertices, goes here, this vertex goes here, and this vertex you can use 2 qubits to simulate this logical qubit here. So I'm using 2 physical qubits to emulate 1 qubit here, right? And the rule is that for each vertex j in the logical graph, I have a subtree that corresponds in the Chimera graph, right? So this is a subtree, right? It's a tree of 2 vertices. Right? And each edge in the logical graph has to correspond to some coupling in C. I mean, that has to correspond to some edge between in the logical graph. For example, 2 and 3 are connected, right? So 2 and 3 is connected through here, and 1 and 3 is connected through this edge here. Okay. I'm trying to read the comments. I don't think there's any question. I don't know what you're writing right now. So the same process is you can do exactly the same process for different kind of graphs, right? Here's a more complex graph that is being embedded here, right? You can see this the pentagon here is being embedded. This is the full graph of 5 vertices. It's being embedded in using all of the physical qubits here in the quantum chip, right? And this is a well-known problem in computer science, right? We have algorithms to embed into other graph. I have a graph, and I want to embed this graph into this, right? And there's a lot of research there that I think you're interested. Really nice research. So this is explained with more details. I just want to stick to the drawing example. So let me give you a concrete example using I have a fly here. Using a well-known problem in computer science known the max-SAT problem. So the SAT problem is a Boolean. I'm giving you a Boolean formula like this, right? If you remember your logic classes, you have, for example, these are called the variables. The variables can be true or false or 0 and 1. And we write the logical formula, using what we call the CNF form, means conjunctive normal form of the formula. That means that we have an AND of clauses. This is called a clause in logic, right? Inside each clause, each variable or literal is separated using ORs, right? A literal it's not a variable, but it's a variable like it could be negated or not, right? So all literals inside a clause are separated by ORs operations, by disjunctions, and each clause is joined by an AND operation, right? And here in the SAT problem, we want to know if there is an assignment of true or false values to the variables that makes the formula true, right? And in the max SAT problem, which is the optimization version of SAT, we want to minimize the number of clauses that are false, right? Or you want to maximize the number of clauses that are true. It's basically the same, right? So I was telling you this is a maximization problem, but we can look at this maximization problem as minimizing the number of clauses that are false, right? If the optimal solution will be 0, right? Because then all clauses are true, and hence the Boolean formula is true, right? So how we do this? So first we have to transform the max-SAT instance to a Kuvo formulation, right? And the idea here is that each clause in the formula, this is called 3-SAT because each clause has exactly 3 literals inside, right? We can talk about 3-SAT we know loss of generality. I'm not going to explain why we said, right? But just follow, just believe me, right? And the idea here is that we take each clause in our SAT formula and we encode it into a Hamiltonian, right? And then each Hamiltonian we're going to add it together to have a total Hamiltonian for the entire formula. And the idea is that we have each small caps h here will be 0 when the clause Cj, the corresponding clause, is true, and will be 1 when the corresponding clause is false. That's the idea here. And we do it using this very simple transformation here. When we have a formula like this, we transform it into a polynomial like this. Okay, so this will give us a degree 3 polynomial. And we can, like I said before, normally you obtain polynomials that are degree 3 or more, and you want to transform it to a polynomial of degree 2, actually. And you can use the known techniques to transform this polynomial into a polynomial of degree 2 or less. Embedding is hard also. It's not an easy problem. Yeah. I'm not really an expert in minor embedding. I think it's finding a minor embedding. I don't know how fast. I think it's you can do it in polynomial time. I have to check that part, right? But I know a lot of people who are working on that field, right? So like I said, you transform each clause into a polynomial of degree 3, and then you sum all those polynomials, right? And after, of course, making each of those polynomials into a degree 2 polynomial. And then you get a total polynomial of degree 2, right? For example, here we have an example of a SAT instance of 9 variables and 39 clauses. And after using our process that I showed you before, we get this polynomial, right? Here you can see there are some clauses that are transformed into a degree 3 polynomial. And after adding the dummy variables to that, adding variables to make it a degree 2 polynomial, you get something like this, right? And the idea is that once you have there, you can interpret this as a graph, because this, for example, you can take this term here means that the vertex 9 is connected to the vertex 24. Right? And the coefficient of this term is the coupling between those logical qubits or vertices in the Icing graph. So what you do then, once you obtain this polynomial or logical graph, you have to feed the coefficients of this polynomial to the SAPI environment that is in Python. So the SAPI will communicate that information to the physical quantum computer. And what you obtain after running once or several times, well, like I said, you have to repeat. You get one result. Each time you run the algorithm, you have an energy level. And remember that energy level corresponds to for the way in which we encoded optimization problem corresponds to some feasible solution in our optimization problem. And when you run several times, you obtain a graph like this, right? And of course, the more times you get an energy level, you kind of say, okay, you're obtaining that solution with higher probability, right? And the energy of the lowest value possible is the one closer to the optimal solution, right? But you obtain something like this, right? And that's why you have to run it several times, right? And here, and then you have to check your reduction, right? To check, okay, this energy level corresponds to which solution in my optimization problem. That's how you get the solution. I was going to give you another example. This is the multi-cut problem. I'm not going into this because I want to go into the multi-objective part now. But the multi-cut problem is really important, especially in quantum machine learning right now. I'm showing you, this part shows how to encode the multi-cut problem in graph theory to the Chimera architecture. So let me now go through to the main point of this talk. Now we know how the quantum annealing algorithm works. how do you program that kind of quantum computers. You don't It's not capable of universal computation. I mean, truly universal in the sense that you cannot do all problems using quantum annealing, right? You can do optimization problems. Maybe you cannot do all of the kind of optimization problems neither, right? But luckily, the main problems that we care about are NP-hard optimization problems. Okay, now let's talk a little bit about multi-objective optimization problem. What I'm going to show you here is what are these problems and how we encode those into the quantum algorithm, quantum annealing framework. And in this part, I was just giving some motivation. This is different set of slides. I was giving some motivation why it's important, optimization. I haven't tell you. I'm pretty sure you know why optimization is important, right? And it appears everywhere, right? And of course, is right now in quantum machine learning, which is really hot topic in research right now. It's a key step, right? Basically, everything in machine learning is optimization. Right? But what is multi-objective optimization? That's something else. So let me start explaining that. So suppose that this is a toy problem. Suppose that I want to optimize two functions, right? Like this, f1 and f2. And the global optimum of f1 is here, and the optimal value of f2 is here, right? What does it mean to an optimal solution in multi-objective optimization? I want to optimize both solutions at the same time. But the problem is that if I optimize only f1, the solution, you can see that f2, when I optimize, if I find the optimal solution for f1, the point of f2 will be something around here. So it's not the best possible solution for f2. It's really bad. But if I optimize f2, I have the same problem with f1. The solution quality of f1 is really bad. So what is an optimal solution there? It doesn't seem to be the best possible solution, because it's the best for here, for example, it's the best for f2, but for f1 it's really bad. So for this kind of parables here, the best solution I can find, is something like in the middle between them. It's a point where neither of them can be improved without making the other worse, right? Here you can see in this region here, when I improve f2, I get a bad, the solution quality of f1 is getting worse. So we have some kind of trade-off between these 2 points here, right? So I cannot really optimize one without making the other worse, right? So in multi-objective optimization, you don't have a single or a single optimal value, right? What you have is a set of trade-off solutions. And in the people working on multi-objective optimization, what they care about is to find this set here of trade-off solutions. You can see this trade-off between the solutions when you graph the solution like this. Others, the question in the comments, actually, in the quantum, I know that I haven't told that part, right? I know QD have a new architecture of more than 5,000 qubits. I've been a little bit away from what are the improvements in the number of qubits in the quantum annealing computer of D-Wave. I know they have a new architecture called the they're not using the Chimera architecture anymore, but they call it the Pegasus architecture. You can find the Pegasus. You look at it in Google, for example, Pegasus architecture, D-Wave, and something like that. You will find information. I know it supports more than 5,000 qubits, and that's it. I think that's the largest number of qubits they have right now. Now, Like I said, you can visualize the trade-off between the two functions I draw before the two parables, and you can see a graph like this. When you get worse in F1, you get better in F2, right? And people, what they want to do is to find all the points over this line, not line, but this curve, right? And people in the field of multi-objective optimization call this the Pareto-optimal solutions. Pareto-optimal solutions are these trade-off solutions that I showed you, right? So it's not a single, it's not a single value in the image of the objective function, but it's a set of minimal points, you want to say it like that. So this the concept of what is optimal changes in multi-objective optimization. And this gets even worse when you have three more or two functions that you want to optimize at the same time. We can draw this really nice here when you have two functions, like, and visualize it on a graph like this, right? But having three, you can visualize kind of three-dimensional, three objectives trying to minimize at the same time. But four is more difficult to visualize, of course. And we care about here about combinatorial multi-objective optimization, meaning that the domain of each function, objective function that I'm trying to optimize is normally finite, right, or discrete. I'm going to care only about finite always, mostly finite. I think it's difficult enough working with finite domains, right? So in general, you can define the multi-objective optimization function like this, right? An optimization function is actually a vectorized function, right? If objective function that you want to minimize, you can try to minimize as a vector, right? In the 70s, the people in computer science started to study vector optimization, which is essentially the same, right? And once I have the objective function, which is a vector, and you want to optimize this vector, find the minimal vector, which is not really minimal. You want to find the Pareto optimal vectors, right? What you want to find here are the non-trivial Pareto optimal vectors. The non-trivials are these points, the points between these two here, right? These are called the trivial Pareto optimal solutions because they are Pareto optimal solutions, but you can just find those points by optimizing each function independently, right? So what I really want to know is the set of solutions here in the middle, right? And those are the non-trivial Pareto optimal solutions. We have some other definitions, like for example, I can have different points x and y in my domain that have the same vector value. So I call those points equivalent solutions. And I'm going to care only about certain kinds of objective functions that I call collision-free objective functions. And that means that I want each objective function. When I compare each point objective function, they are separated by a distance of lambda at least, right? You have to look something like this, right? It doesn't need to be a parable or anything like that. I just want each solution, because remember, this is a combinatorial optimization problem. I want each solution to have some distance of separation between them. And that's really important. It will be important later because I'm going to tell you later, right? It's really important. So one very common technique that people have been using since many years ago in combinatorial optimization, multi-objective combinatorial optimization is and the most natural way to solve a multi-objective problem is to take the vector or the set of objective functions that you want to solve and construct a convex combination of each objective function and transform it into a single objective function, right? And then you minimize this, and you automatically obtain a Pareto optimal solution. It works really well, but it has a key problem. Most of the solutions that most of the Pareto-optimal solution cannot be found using this technique, and that's been known since many years. You can find some, but not all of them. Actually, most of them, because the set there is a theorem. I don't have the reference right now in my head that says, for example, that the number of the set of optimal solutions that cannot be found by using the linearization technique presented here grows exponentially faster than the set of solutions that you can actually find using the linearization of objective functions. So as long as if you domain is really big and you have more objective functions to optimize, this linearization method really is not the best. So people in optimization, multi-objective optimization, have been studying a lot of techniques from artificial intelligence to solve the optimization problem. And of course, in this work, me and my co-author, we propose the first quantum algorithm for multi-objective optimization. Let me show you one of our first tries, because when we attempted to solve this problem, right? The first try was to actually use Grover's algorithm, and it wasn't really good. I'll tell you about it. The idea was to Grover's algorithm. Grover's algorithm is a problem of trying to find an object or a set of objects is of a big bag, right? And the idea here is that essentially Grover's algorithm is just about rotating a vector from, for example, some initial state to some target state, right? And what we did was to make a direct adaptation of some initial attempts of doing quantum optimization using Grover search. But I don't want to explain the details here, and because I don't have much time, right? I think, but it didn't go very well. What we did was to take, for example, like I said, the initial. Or I'm getting messages. I think I have to disconnect. The noise bothering me. You have to take this Grover's algorithm. We use the Grover's technique to optimize single solution optimization problem, a single objective optimization problem, and we generalize this to the multi-objective optimization problem we call MOGAS. And it did work really well. Actually, when we did some results, for example, we did some comparisons between a classical optimization algorithm called the NSGA2, and actually, here you can see that the NSGA2, which is a classical algorithm, it behaves. I mean, our optimization is a little bit better in the quality solution. So it's just 1% difference, and we try in different kind of instances, right? And it always finds the Pareto-optimal solution faster than the classical algorithm, right? So it suggests that there is some speed up, right? But I mean, we can only do these experiments using very few qubits. We have to try for more, because simulating even it was for 10 qubits the experiment, and it really takes a long time, right? So we need to do a lot more work that, right? Increase the number of qubits, something like that. But we weren't really happy, because it was a really ad hoc technique. We just took the Grover search algorithm, make it a multi-objective. It was more of a kind of a heuristic algorithm. We couldn't prove anything. We couldn't prove convergence. Convergence is kind of easy to prove, because you always have a positive probability of improving the solution quality. Right? I want to spend more time discussing how to solve multi-objective optimization problem using quantum annealing. Right? So this part I already explained, right? So I'm going to skip this part. And what we did here was we were able to prove the following, right? So if I give you an multi-objective optimization problem that is collision-free, that's the definition I gave before, that said that there is some separation between each point in each objective function, and if there are no equivalent solutions, then you can actually use the linearization technique to solve the you can use the linearization technique to solve quantum optimization algorithm using quantum annealing algorithm. That's basically what this theorem says. But we have to what I call structural restrictions. First, each objective function has to be collision free. There have to be that separation between the point, a little bit of separation, and you cannot have equivalent solution. That means different points in the domain have the same image, right? And that's very important, because when you allow that kind of things in the multi-objective optimization problem, it happens that you cannot apply the adiabatic theorem, because the adiabatic theorem, one main hypothesis in the adiabatic theorem says that there have to be the eigenvalue have gap. I mean, it's about the multiplicities of the energies in the Hamiltonian. You need to have a multiplicity of 1 for each eigenvalue in your Hamiltonian, and if you allow these kind of things here, you cannot get that, and hence you cannot apply the adiabatic theorem. So the proof of that theorem, what we do is to encode its function fy in each individual Hamiltonian, and then we take a convex combination of those to make an entire Hamiltonian, right? And then what we do is we encode each objective function like this, right? And just start, for example, in the ground state of this Hamiltonian here, this will be our problem Hamiltonian, and then what we do is to start in the ground state, do some adiabatic evolution, measure, and then you obtain the optimal solution to this linearization of the multi-objective problem. And okay, and this theorem by Ambani and Riget, what it says is that it bounds how much time you need to run your quantum algorithm to actually obtain with high probability the solution to the Diabatic algorithm, right? I skipped a lot of details because I already have spent 1 hour. So, and then what we did was to try to prove the theorem experimentally by trying it in the 2 parabolas problem I showed you before, right? And the idea was to take 2 parabolas. These are not really parabolas because we're talking about this discrete problems, right? Well, it has the shape of a parabola if you join all the parabolas, but these are really discrete points that look like a parabola, right? I have a question here. For the sake of curiosity, there is a comparative analysis between a classical computation. Yes, there are. There are several papers. The original paper by Farhi and authors about the adiabatic algorithm have comparisons with the Max and other problems. But it's all heuristics, right? And there's no way to give a I'm more interested in theoretical bounds in the time, for example. And there's nothing about it. So the evidence, the experiment suggests that it is really faster, right, than just a classical algorithm. But there's nothing. I mean, no theoretical evidence, right? We suspect there is, right? So, like I told you, what I did was to encode these two parabolas problem into these 2 Hamiltonians, and join it into a single final Hamiltonian, and take this construct a Hamiltonian using, but our technique basically is doing is linearization, right? But and it didn't tell you what kind of multi-objective optimization problem you can actually solve, right? And what we care about, when you care about running time, is the eigenvalue gap between the lowest eigenvalue of the Hamiltonian and the second lowest. That that's what tells you, using the theorem by Binance and Regev, how much time you need to run the quantum annealing algorithm to actually obtain a optimal solution in to a problem, right? And here, for example, we saw that for the two parabolas problem, the eigenvalue gap decreases like this, right? So this is something that people really care about in quantum adiabatic algorithm, to see how the eigenvalue evolves in time when you are solving an optimization problem. In order to transform, it's really fast. You want to transform. The question here is, how much time do you spend? Basically, you're asking about the computational complexity of transforming a degree n polynomial to a degree 2 polynomial, and it's really fast. You can see the techniques is just it should be around linear time, or definitely is polynomial time. I think it's linear time because you just have to check the shape of the polynomial and add the extra variables. So you just have to apply the formulas for the methods, so it's really fast. So what we have here are actually many open problems, right? These are just a few I really care about, because when we encode our multi-objective optimization problem into a Hamiltonian, what actually we are doing is what I told you that was bad at the beginning, which is linearize the multi-objective optimization problem. Right? So we tried really hard to find a method that avoids that linearization, because, like I told you, the linearization technique cannot find all Pareto-optimal solutions. So we need to think of we need a new idea how to encode a multi-objective optimization problem that avoids linearization, or at least that help us find problems, optimal solutions, or Pareto-optimal solution that cannot be reached by the linearization techniques. And we need to be able, another thing I'm really interested about is how to take out some of the conditions in our theorem. Like we need equivalent, we cannot have equivalent solutions, and we need collision freeness in our optimization problem. I think things like that, right? And that's basically it, right? So I think I spent 1 hour and 5 minutes on this. So thank you very much. That's all. That's it for me. I don't know if there are more questions. I tried to ask another question. I have the comments here, and I'm looking at the comments.
Well, thank you, Marcos. Thank you for your nicely talk. Well, you answered the questions during the presentation, and if one of our listeners have another question, please put in the chat.
I don't think I answered this question. There's a question that says, I mean, there is a price for the approach, right? Maybe the question is, from what size of problems is it worth to use the quantum machine? And that's a big problem, actually, because right now people are writing papers on how to. They actually forget about the quantum machine. People are writing papers about how to transform optimization problem into a Kuvo problem, because that transformation actually requires a lot of creativity. And when you transform to a Kuvo problem, you get a single optimization, a single objective function that probably has a lot of slack variables, because there are no restrictions. So you need to have those slack variables, right? And you have to find a way to encode the problem into a Kuvo model that has the smallest possible number of slack variables, right? So that requires a lot of try and error, right? Because the more slack variable you have, the more qubits you will need, right? And you don't have a lot of qubits either, right? And that's a big problem. So the transformation problem, the reduction has to be really good also. And there's a lot of research people are showing how to transform into Kuvo NP-hard optimization problem into very, I don't want to say the word correct, but it's efficient, but with the smallest possible number of slack variable. So the more slack variable you have, the more qubits you need. And that's something limited right now.
Well, thank you for this answer. I think that only congrats.
Okay, thank you very much.
Thank you again for your talk. We really appreciate your presentation, and I hope to work with you in the future, in the near future. We are also working in SAT problems and adiabatic computation, and I expect to have another conversation with you about this subject.
No, okay. We're interested. Yeah.
Okay. Thank you very much, Marcos, for your presentation. Thank you for accepting the invitation again. And well, we stop our transmission now. We return 16 hours, 16 horas, 16 o'clock, 16 o'clock, for the mini course of Evandro, ok? Então a gente volta de novo às 16 horas com o mini curso do Evandro. Então, obrigado pela presença de todos e até à tarde. Até mais. Obrigada, Marcos. Thank you, Marcos. Bye-bye.
Bye-bye. Thank you.